Okay, hello. Welcome to the week 2 of Math 270. So we already covered section 1.1 and 1.2. So the target this week is to cover section 1.3 and 1.4 and to prepare you for your quiz. Okay, so I've already posted the practice quiz for you. Later on, I will give you the solution to that practice quiz. Okay, and the actual quiz will be posted. You know that the quiz is going to be taken quizzes, but the tests are going to be on Zoom. So over the weekend, I will post the quiz for you, and it's going to be due on Monday. And we collect the assignment on the day of the quiz. So you have to submit your assignment by Monday as well. And I've already posted the numbers are going to be due for you. So this week you should be able to, to finish 1.3, 1.4. In 1.3 and 1.4, and for the rest of this chapter, we are going to look into the operation with matrices. Okay, we talk about it in order to solve a system of equation. Remember, we introduced a tool. The tool was augmented matrix. So we're going to look into the matrix. What is going to be the matrix? Matrix is a kind of, it's a function. It's a function that take an order pair of the integers into a number, okay? Or we can summarize the given data in a short form. That short form is going to be a matrix. So we use a matrix as a function. So what we can do is we can talk about addition, subtraction, multiplication, all these type of operation with the functions. So we are going to look into this operation in section 1.3. It's an easy section, so I try to give you a brief summary of this section today. Okay, and 1.4 is a little bit more technical, but it's not bad. So by the end of this week, you should be able to answer the question regarding 1.1, 1.2, 1.3, and 1.4. And as usual, if any question, you can come to my office hour or email me. But before coming to the office hour, you better send me an email so I'll be there, answer any question or any concern that you have. Okay, let's see what is going to be the topics in this section. It is a section, but it's going to be the foundation of what we are going to do in future. So this is it. Let's see. So this is going to be our section 1.1.3, and we're going to talk about the metrics. Okay, metrics operations. Uh, the linear algebra would be divided in two parts. One part we call it computational one, and the other part is going to be the abstract for future. The computational one dealing with the matrices. And it's a nice one. Some people they like it. It can be done, in finite dimensional. When you go to the infinite dimensional, we change the matrix into a function. It is a function, okay? We call it a linear transformation, and we do the job over there. Okay, so what is going to be a matrix is just a function. A matrix in brief form is going to be is an ordered, okay, it's going to be an ordered rectangular collection or rectangular array of numbers. It can be also arrays of functions in future, but for the time being, just numbers. Okay, so a matrix, okay, a matrix with m rows and n columns. Okay, n columns is going to be denoted by, so it's going to be denoted by the notation that we're going to use is this notation, a equal to the aij we write this expression. I think this is what it is in your book. Or I use this expression, Aij. I use parentheses rather than bracket. So from time to time, this is the way we do it. But we are going to give you the information that this I is going to be the rows, which are going to be between 1 and m. Okay, and the n would identify the number of the columns. Okay, so j is going to be between 1 and n. Okay, so this is going to be the metrics. Okay, instead of writing all of them, we like to give you some that was going to be a general formula that can identify the a and j, or we just put them together as is. Okay, so of course each of these numbers, if you like, each aij is going to be a number, is going to be called an entry. Okay, this is called an entry. This is going to be an entry of the matrix. Okay, we identified the location by I and j. We have an expression that's going to be the size. You have to know this one. And the size of A, the matrix A, is going to be defined. Okay, it's going to be defined by m cross n, or m times n. That's the size. We don't multiply it, of course. So we say the size is 3 by 2, 2 by 3. Okay, this is going to be the one. If okay, so A is defined by m times n. So we say that so in this case, A is going to be, A is n, if you like, m by n matrix. Okay, that's going to be the one. If this m is equal to the m, we are going to have a square matrix. If m is equal to n, then A is going to be called, A is called a square matrix. Okay, it's going to be a square matrix. So a square matrix is when the, okay, a square matrix when the m and the n are going to be the same. Okay, as I told you, it's going to be a function. It's going to be a function. The domain of this function is going to be kind of, it's coming from R2 if you've done, okay, and or cross product, if you like, Cartesian product. Okay, we get an ordered pair of the numbers 2 and 3, and then you assign, okay, aij. So the matrix is going to be a kind of function, really. Okay, it's going to be a function. So what you do in this function is, if you like, you put the, you start with the aij and you assign a number to that ordered pair. So we can talk about it as a function too. Okay, so your job, your first job is just get to know it. In your book, they give you some matrices and they ask for the size. So the example, for example, if this is going to be the first one we have a 2, 3, 2, 3, 1, -5, and then we get a 2, 5. As you can see over here, we are going to have 3 rows, 1, 2, 3, and the 2 columns. So this is going to be a 3 by 2 matrix. This is the way we're going to call it. Okay, that's a first one. And then if you have something like b equal to, if you have a 2, -5, 2, -5, and I'm sorry, 2, -5, and this is going to be 7, 5. So in this case, as you can see, you have 2 rows and 2 columns. So this is going to be is a 2 by 2, 2 by 2 matrix. Okay, it's a square matrix. Okay, B is a square matrix. Okay, so that's going to be a square matrix. Okay, and sometimes we have some special one that we're going to use in future. Okay, so if you have a matrix with one row only, you see 1, -3, and that's a 4, and then -5. You see this matrix would have one row but 4 column. Okay, so this is going to be is a 1 times 4. We call it row vector. Row vector. So we're going to use this type of notation through the through the course. And you may have some if you have only a single column. So for example, if you have a D which is equal to the -5, -5, 2, and 8, as you can see, you have only one column. So in this case, this is going to be is 3 row 1 columns. It's going to be 3 by 1 column matrix. Okay, so it's going to be column vector or column vector. Okay, when you have a single row, or we call it a row vector. If it's going to be a single column, we call it a column vector. So that's it. So we have a new tool. Okay, we have a new tool, a function or just a matrix operation. So in order to be able to talk about equality, so we have to determine when are you going to assume that two matrices are going to be equal to each other. So two matrices are going to be equal to each other if the corresponding entries are going to be the same. Okay, it's like two functions are the same if they have the same values and of course the same domain. It's the same thing. Okay, so the first operation that we're going to take care of, we're going to take about the matrices equality. Okay, this is it. Matrices equality. Okay, so two matrices are going to be the same if they have the same entry. They have to have the same size, of course. Okay, so suppose we have two matrices. Suppose A is equal to the matrix like Aij. Okay, this is going to be one of them. And from time to time I use bracket and parentheses, same thing. Okay, Bij. These are going to be M by N. Okay, so they are going to be R, same size, M by N matrices. If this is going to be the case, then we define the equality. Okay, we are going to say that A is equal to the B if and only if the corresponding entries are going to be the same. So if and only if Aij is going to be B equal to the Bij for all I and j. Of course, I is going to be number of the rows between 1 and m. Okay, and j is going to be number of the column. So it's going to be between 1 and this would be useful. You have a couple of problems in your assignment that they are going to, okay, they are going to give you uh, a kind of an equation containing the matrices, and then there are some parameters, some unknown that you have to find it. So you're just using this fact that they are going to be equal to each other if they are going to have the same size, and the corresponding values or entries are going to be the same. Okay, so that's matrices equality. As soon as we take the equality, then you can talk about kind of operation that you are interested in. Operation like addition, subtraction, multiplication. Then you can talk about property of addition, multiplications, commutative, associative, etc. Okay, so that's the equality. So now we can talk about addition. Again, two matrices with the same size. It's like a function. You can add them together pointwise, we say, by adding the corresponding, okay, values. So the matrix addition easy. So it's going to be matrix, okay, matrix addition of matrices, matrix addition. Okay, the same thing. So if, again, A equal to the Aij, one matrix, and the B is equal to the Bij, this is going to be another matrix, are going to be our matrices, are, let's say, M by N matrices. Then we can define the sum. Then you see we can add them together. We can have A plus B. So A plus B is going to be, we have the same matrix, Aij. We're going to add the corresponding, okay, the corresponding entries, if you like. One by one, if you add them together, you are going to have a matrix with this is going to be, okay, the term of your matrix, if you like. Okay, you have the same size, so we pick each entries, the corresponding entries, then you add them together. Okay, so that's going to be addition, and you can do the subtraction, easily the same thing. So that is going to be adding or subtracting matrices. Okay, so make sure that they have the same size, otherwise you can't do it. Again, you have some problems in your book, and this is it. They just ask you to do the addition. Okay, so you may ask to simplify or add. Example, the first one, suppose you want to add this one, 1, 2, negative 4, and then you have the 0, 3, and negative 1. Okay, this is your first matrix, which is a 2 by 3. Then you want to add it. Okay, you want to add it the second one, and that's going to be negative 1, 0, 2, and you have the 1, negative 5, and 3. Okay, you want to add them together. This is it. You have the same size, so you just add the corresponding okay, entries. So for example, this is going to be 1 and negative 1, which is going to be 0. You add them together. This is going to be 2 and 0, which is going to be 2. And then negative 4 and 2 would be negative 2. Go to the first one, 0, second one, 0 and 1 would be 1. 3 and negative 5 would be negative 2. And the 3 and 3 would be 6. So this is going to be the resulted matrix. Okay, so we have a 2 by 3 and 2 by 3, and you can do it. Okay, but if they give you this one, okay, if you want to add 1 and negative 3, 1 negative 3, and this is going to be 2 and 4. Okay, this is going to be a 2 by 2, and if you want to add it, to the negative 5, 4, and 6, and this is going to be 3 and the 7 and the negative 1. As you can see, this is going to be the case. So this is a 2 by 2 matrix, the size, and this is going to be a 2 by 3. So you cannot do it because they don't have the same size. Okay, so this is going to be is undefined. Okay, this is going to be undefined, or in short, undefined. Okay, so in order to add or subtract the matrices, we have to have the same size to be able to do it. Okay, so that's going to be matrix addition. And then the multiplication, we go with the scalar multiplication first. So what's going to be a scalar? Scalar means the number. The number can be okay, real number for the time being, and in future it can be also a complex numbers. So what is going to be a scalar multiplication? Okay, so a scalar multiplication, you get the number and you want to multiply by a matrix, you just multiply all the entries of the okay, the matrix by the number. So the resultant matrix would have the same size, but the entries are going to be just multiple of the original one. Okay, so there you are. If we get the matrix A, if the matrix A is going to be Aij, okay, and is of course is an m by n matrix, m matrix, and C is a number. Okay, C is a number, so C is any scalar, if you like, a scalar. Then you see if you multiply the A times C or C times A, you just multiply those scalars together. Okay, so this is it. It's going to be C times the entries. So we're going to have the, you know, you have the new matrix. The size is going to be the same, but the entries will just multiply by, you know, multiply by C. Of course, this is going to be where I is going to be the number of the, okay, rows, and the J is going to be number of column. Okay, scalar multiplication. You get quite a lot in your book that they ask you to do it. Okay, so standard example is going to be the following. The the way we have it. Okay, so you know we can use the scalar multiplication, of course, to define the subtraction. Okay, just remind you here that I've already talked about subtraction, but officially you must talk about it now. You see, so if you want to find the a minus b, this is like a plus negative 1 times b. I already talked about it. I just change, you know, change the sign of each entries. So that's the justification for, you know, you have to have the scalar multiplication first. So tell us what you mean by a negative times b, and then get the result. Already did this one. Okay. So the example, you have some in your assignment, or from time to time we are going to do it. So if you want to multiply, for example, 2 times, okay, 2 times a negative 2, 1, and 3, and then negative 5. So we just multiply each entries by 2. So basically this is going to be 2 times negative 2 is going to be negative 4, and the 2 times 1 is 2. 2 times 3 would be 6, and the 2 times 5 would be a negative 10. Okay, so that would be the final answer. Okay, so these are going to be easy, but we are going to use it quite a lot. Okay, so that's the first part. And the second part, officially, this is how you'll be given some problems. Okay, so they give you A and the B. So if A is equal to, is a 2 by 3 matrix, so it's going to be negative 3, negative 1, negative 1, 4. And this is going to be 0, 2, and negative 5. So that's going to be matrix A. And then you be given the matrix B. Okay, so it's going to be matrix B, which is a negative 1, 0, 5. And we have the 4, negative 2, and 1. Then they may ask you to find some values of this matrix. And then you may ask, find or compute, let's say 2a minus 3b. 2a minus 3b. Okay, so we do the scalar multiplication first, and then you do the addition. Okay, so and this is it. Briefly, that's what would happen. So if you want to find the 2a minus 3b is equal to, I multiply the a by 2, So that give me 2a, which is going to be a 6, 6, and negative 2, 8, and that would be 0, 4, and negative 10. So this is going to be the first one, is a 2 by 3. Okay, so I'm going to subtract it, minus 3. I can multiply by negative 3, then I add here, okay? And this is it. So I multiply the second one by negative 3. So that give me a positive 3. This is going to be 0. It's a negative 15. Okay, so it's going to be negative 12, 6, and the negative 3 here. Okay, negative 3. So there you are. Okay, so I multiply by those scalars first, then I'll add them together. So what's going to be the final answer? The final answer is going to be, you see, this is it. That give me 9. So this is going to be 9. This is going to be a negative 2, 8, and 15. That give me negative 7. And here that give me negative 12. 4 and 6 would be 10. Negative 10, that give me negative 13. And it. Okay, you have a couple of them in your assignments. Okay, so I multiply by those scalars first. I multiply the first one by 2, the second one by negative 3, and then I add them together. When you want to add, you add these corresponding entries. Okay, corresponding entries together to get the final answer. Okay, so that is the addition. It's like a operation with the functions. So that was a scalar multiplication. Now what's the actual multiplication? This is different. So far, everything is like an ordinary function. Okay, we add, we subtract, we multiply by a scalar number. In a case of the multiplication, you know that in calculus, we multiply two functions by pointwise. I mean, if you want to find f of x times g of x, you find the f of x and you find the g of x, you multiply them together. But that type of operation is not going to be good for the matrices. We did have another operation, binary operation with functions in calculus, and that's a composition. Okay, so the multiplication of the matrices is a kind of composition of composition of two functions. Is going to be composition of two functions to get the this idea of a matrix multiplication. Okay, just remind you that, you see, this is going to be, so that's a tricky one. What is a matrix? Okay, what's going to be matrix multiplication? Okay, it's nice to get to recall from algebra to see what's the origin of this operation, because it's going to be very important for us. Okay, so I just recall, if you like, I recall the composition, if you like, the composition of two functions. Okay, so we have a function f, which is defined, let's say, from x to y. This is one of them. And then you have the second one, and you have the function g. Okay, function g, which is going to be defined from y to x, or y to z, if you like. This is a situation you're going to have. Okay, so the function f is defined from x to y, and then the function g is defined from g to z. If this is going to be the case, then we can define a composition of these two functions. Okay, so what is going to be the composition of the function? So we define the g of f, if you like. G of f would be a function that's going to be defined from x to z. You see, it's going to be x to z. So how we're going to define it is going to be g of f of x, which is going to be g of f of x. That's how we define the composition of two functions. Okay, so as we operate, you see we operate the f first. You see we get the x here. So we drop it into the f function first. You see this is going to be the f function. F function apply, we define the f into the x. Okay, we got the f of x here. We got the f of x, then we bring the g function. So we bring the g function, then we operate the g to the f. So that gives us g of f of x, which is g o f. Okay, it's a kind of a multiplication, not multiplication, it's a binary operation. Binary operation to do it. It's like, you apply for a job. You apply for the job. So first they offer you a test, if you like. If you pass that test, then they ask you for interview. Okay, that's going to be the one. So it is the first place. This first action must happen, then you can go through the second one. So if you don't pass the first one, you cannot go to the second one. Okay, that is going to be how we're going to do it. But as you can see, this f of x is in the range of the f, if you like. It's a point in y. So in order to be able to go to the g, you must make sure that this f of x is in the domain of the g. That's why these two portions must be the same to be able to operate. Okay, so in the case of the matrices are going to be functioned. Okay, they are the same thing that you are going to have. So if you want to change it into two matrices, the first one is going to be a matrix. Okay, and this is going to be, see exactly, this is what will happen. Okay, now if the first function, okay, I call it aij if you like. If aij, if a equal to the aij is going to be my first matrix. Okay, is an, okay, if this is going to be something like m by r, okay, m by r matrix, okay, is going to be m by r matrix. That's the first function, and I need the second one. So the second one is going to be bij. Okay, is going to be, remember, in between this domain and the range. Let's coincide so that you'll be able to take through it. So this is going to be, okay, this is going to be is an r by n. You see these two must be the same. Exactly, it's happened for the composition of two functions. Otherwise you can't do it. So if A is an m by n matrix and B is bij is an r by n matrix. Now that composition over here, they call it the multiplication. The product, if it's going to be the same, then we multiply them together like a GOF that we talk about it. So the product from the function point of view, just a composition. The product AB, you see you start with the B is going to be M cross R. Then you go to the other one is, you see, start with the B, which is going to be R times N. Okay, this is it. If you put them together, okay, so it's going to be, this is going to be AB. So we pick something from B. Okay, then we pick something from B, which is going to be R times N. Then we go to the other one. We multiply together. So this is going to be the product AB is going to be is N. Okay, This is going to be an M and M by N matrix. Now we're going to define it. Defined by, or such that, okay, it's going to be such that what? So if it's going to be AB, if we call it the new matrix, this matrix is going to be C, and we call it Cij. Cij, where now what is going to be the multiplication? It's a composition of two functions that you put it over here. Now we have a new matrix. This matrix Cij is going to be M by N matrix. Now we're going to define the entries of this matrix. If you want to find one of the, the entries Cij, so what we're going to do, we are going to multiply the I, okay, the I row from the A, you multiply by the J of the column, and then you add them together. So if you multiply something, the I rows from the A, so it's going to be, okay, you start with the I row. This is I, you see, you start with the I row of the matrix A, I, AI, you see, I row first column, 1. Okay, you multiply by the second one is going to be the J column of the B, so it's going to be B, okay, B, 1J. Okay, this middle one are going to be the same. Then you continue. Okay, you continue in the I row. Then you just keep going. You see, it's going to be a I rows, the second entry, second column. Then you multiply by. Okay, this must be the same, but you stay with the J column, and you continue. This is going to be A3. Okay, A3. Sorry, AI. The I would be the same. And that give you 3, but B3, B3J. And then you just keep going. Keep going. Okay, how many columns are you going to have? You see your A is M by R. So the last column would be R. And this is going to be B, R, J. Okay, so it's going to be, you multiply the ith row of the A, multiply by the J column. J column of the, okay, of the matrix B. This is a kind of multiplication that we call it inner product. We've done something similar in R2 and R3 in calculus, okay, in calculus 3 or in general. So if you are familiar with that, okay, or just, in sigma form, in short form, if you like the short form, this is going to be the case. You see the row of the first one is going to be I. So you have to change, just move on to the column. And this is going to be the same thing for the B, and this is going to be J. But K would goes from 1 to, okay, 1 to R. In practice, it's easy to operate. So you pick the J column if you like. You see this is going to be the J column of this is, you see this is the first matrix. This is the first matrix. You just consider consider this column. This is it. This is row. Okay, this is the I rows. And what you do is, this is going to be your second matrix. Okay, this is your second matrix. So what you do is, you are going to multiply this one by the, okay, multiply this one by the J columns. Okay, so this is it. You multiply by one, you just keep going. Okay, so you continue this one to get to the new matrix. So this new matrix, your I would be, this is M by N. So I is going to be between, okay, sorry, that's I. I is going to be between 1 and M, and the J, as usual, is going to be between 1 and N. Okay, so that is going to be the case. So if you are familiar with those type of ideas, okay, or we have just said for future, you can say that the C, okay, the Cij, if you like, is going to be is the dot product. If you are not, that's fine. We talk about it later. Is going to be the dot product of the ith row of okay row vector, if you like, row vector of a and the j, okay, the j column, column vector, column vector, column vector of b. I'm going to give you example to see it. So its idea is really just the composition of two functions. That's why you see this type of operation. You can write down in function notation and exactly get, exactly what we, okay, exactly what we proposing over here. Okay, so that is going to be the case. I'll give you an example to see how we're going to operate with the multiplication. So you have to check the size first. You see for the function even, you should be able to carry it, okay, the middle one, uh, with the size if you like. The first one's going to be n by r, the second one must be r by n. It's like the range of the range of the first function, the range of the first function and the domain of the other one must be the same. Otherwise, you cannot go through the second machine. Okay, so that is the reason. You see the functions. This is the range of the first one or the codomain, and this is going to be the domain of the other one. Otherwise, you can't do it because this f of x should be able to go through the second machine. If they are not going to be the same, you cannot do it. Okay, so that's was the first condition that you check, and then you do the multiplication. Okay, let's give you an example to see how we are going to operate. That's a very interesting operation. So it helps us quite a lot. In this just the beginning, really, just when you want to generalize the notion of a matrix into the so-called linear transformation. We always say product, but we mean composition in this case. Okay, so there you are. This is how you are going to be questioned on this one. We give you one of them to find, and you have quite a lot in your. You can do the quickly the assignment of 1.3 because just all operational one. By the end of the today, you can do quite a lot of them. Okay, example. So this is it. You've been asked to compute. Okay, compute the product. The product. So what's the product? The first matrix is a -2, -2, 3, 2. Okay, and that is going to be 4, 6, -2. That's the first matrix. As you can see, it's a 2 by 3. What's the next one? And the next one is this one. It's a 4, -1, 2, 5. And we have a 3, okay, 3, 0, 1, 1. And we have a -2, -2, 3, 5, and okay, 5 and 3. That is what we are going to have. Okay, 5, 3. So that's going to be the second matrix. Okay, so this is it. You want to multiply it first, you check to see if the condition is satisfied. Okay, so the solution, if you want to do it, check the size first. Check the size condition first. The size condition first. Okay, As you can see, the first matrix is going to be 2 row 3 columns, so it's going to be 2 by 3. That's the first one. Okay, the second one is 3 by 4, 3 by 4, like the one that we talk about it. The range of one function, if you like, is the same as the domain of the other one, so this means it's possible. Okay, it's possible. So the left, so when we multiply together, the result is going to be, okay, so the result is going to be a 2 by 2, 2 by 4 matrix. So that give you the idea how we're going to do it, and that help you quite a lot so that you're not going to miss it. If this size condition is not satisfying, you're done. You are not going to be able to continue, and just leave it, and that would be the end of the problem. Okay, so we are going to do it as we talk about it. You are going to get the first row. You see, that's it. And you get the first row, and you just multiply it by all the columns. You see, that's it. You multiply by this column, and then you continue to getting all these. Okay, when you're done, you come back and you do the other one, because the 2 by 4, 2 by 4. Okay, so there you are. This is going to be the result. Okay, so the product is going to be equal to, if you like, so 2 by 4, you multiply, you go forward, you know that you are going to have 4 columns. So this is it. I'm going to show you the first one. If I multiply this one, -2 times 4 would be a -8. 3 times 3 would be 9, and that would be a -4. So that's a first, okay, that's going to be first entry. So I need 4 columns, so I'm going to continue. Okay, this is it. I'm going to have 2 rows only, so this is it. I continue multiplying the row by column, so we multiply. So multiply these two together, that give me 2. Okay, that give me 2. 3 times 0 would be 0. We do it right away by explaining. And then 3 times 2 would be 6. Okay, so that's a multiplication of this row and the second column. Continue this row and the third one. -2 times 2 would be a -4. Okay, then 3 times 1 would be 3. It would be 3, and the 2 times 5 would be 10. So that give me the third one. Okay, continue getting to the fourth one. -2 times 5 would be a -10. Okay, a -10, a +3, a +3, and okay, a +6. So that give me the last, okay, the last column. So I take the first row and just multiply by the columns. I just move forward. So as you can see, this is going to be the first row, first column, second column, third column, fourth column. Okay, now come back and repeat it for the other one. We repeat it and we get the second row. The second row multiply 4 times 4 would be 16. Okay, it would be 16, 18, 16, 18 minus 4. Okay, or +4. +4, negative. Then we get the next one, and next one is going to be -4. Okay, -4, 0, and -6. Okay, and the third one, 4 times 2 would be 8. Okay, the third one, 8, 6, 8, 6, and -10. Okay, and the last one is going to be 20. Okay, 20, 26, and -6. Okay, 6 times 1, 6, -2 times 3, 6. Simplify it, that give you the product. Okay, so that's it. So what we have over here, this is going to be a +1, -3, -3, and that is going to be 8. And this is going to be 9. And the last one is going to be -1. Okay, -1. And this one over here is going to be 28. 28. That is 20. What was this number that we got? I made a mistake here. 4 times 4, 16. 6 times 3, 18. That's 18. Okay, that's 18 because I should get 38. Now I'm going to have a 38. Okay, that's a 38, and the next one is going to be negative 10, negative 10, and this is going to be, okay, that's going to be a 4, and the last one is going to be 20. So this is going to be the result, the product of two matrices. Not difficult. Sometimes it's messy. We are going to do it just a couple of times. Make sure you are ready for it. Okay, so this is it. You get some of them in your book. This is the way you're going to answer it. You have some problem in your books. They just give you the size and they ask you to, okay, to investigate if it's possible. I just want to make sure you know what you are going to do. Okay. So they give you this one. They said, suppose, okay, suppose A is a 2 by 3 matrix, okay, and B is a 3 by 5, okay, 3 by 5 matrix, okay, 2 by 3 and 3 by 5, and they ask you to find the size, okay, find the sizes of AB and BA, okay, if they are defined. You have a couple of them in your book, so this is the way you are going to answer it. Okay, we talk about it. So the solution is going to be, if you want to consider the size of the AB, so you have the 2 by 3, this is the first one, and you have the 3 by 5 composition of two functions. As you can see, these are going to be the same, so it is possible. So the conclusion is going to be, you get a 2 by 5 matrix. Okay, so AB, it's possible, is going to be a 2 by 5 matrix. It's possible. Okay, and the second one, it's not possible because the B is 3 by 5. Okay, and that's 2 by 3. So as you can see, the domain and the range that we talk about it, you see this one, it's going to be 2 and the 5. So they are not going to be, we can't do it. Okay, so the BEA is undefined. Okay, it's going to be undefined and we can't do it. So when we get to this type of problems in your book, so don't be surprised to get these operations. Okay, so quite a lot of problems with these operations. You just do it. So we did the addition, subtraction, multiplication. We are not going to have a kind of division that you like, but we introduce something similar to that one. And that would be the inverse of a matrix, but you have to wait for it. There are some other definition, operation of a matrix that we are going to use quite a lot in future. So we are going to define one of them. Okay, these operations are going to be very useful, and everything we talk about is going to be extended to the function type in future. So if a matrix is given to you, then if you switch the row and the column, if you switch the row and the column of a matrix, you are going to have a new one. This new one is called the transpose matrix. Okay, it's very popular. We are going to have quite a lot of operation with this one. So why not? We define it right away. I talk about it. We are going to prove something in each section as we go on. So this idea of a transpose would be useful. So you can use it to get, okay, to prove if you like. So we wanted to know it. So what's going to be transpose? Transpose, new operation. of a matrix. So if you switch the row and the column of a matrix, the result is going to be a new matrix which is called transpose. So if A equal to the Aij is an M by N matrix, okay, M and N matrix, then the transpose. Then the transpose of A is going to be denoted, notation is denoted by A transpose, you see A transpose, or this one. I usually use the second one, okay, A transpose. And it's going to be defined as a matrix is defined by, we switch the row and the column. So if A is equal to the, so if A is equal to the Aij, okay, so what's going to be transpose? So the A transpose, you switch, is going to be AGI. Okay, AGI. You switch. Of course, you know that this is going to be an M by N matrix. This is going to be an N by N matrix. Okay, so this is it. I between 1 and M, and the J between 1 and N. So you note that A transpose is going to be an N by M matrix. Okay, so basically, if you like, this is it. So if you like the rows, okay, the rows of A become the column. Okay, the columns of, become the columns of A transpose. A transpose. Okay, easy, but such a useful idea. And you're going to use quite a lot. Get used to it. Okay, so your job is easy. A matrix would be given. They ask you to transpose of a matrix. And get quite a lot, again, in the assignment of 1.3. So the example, they ask you to find the transpose of each matrix. Find the transpose, okay, of each matrix. No condition is needed. You'll be able to find the transpose right away. Okay, the first one, this is it. A is equal to, it's a 2 by 3 matrix, 1, 4, 5, and the negative 3, 2, 7. Okay, so this matrix is 2 by 3. You want to find the transpose, just switch. You are going to have a 3 by 2 matrix. Okay, so this is going to be a 2 by 3. Okay, just for information, solution A transpose is going to be a 3 by 3 matrix. Okay, 3 row. So just switch. You see, this is A transpose. This is the first column. You change it into the, okay, this is the first row. You change it to the first column. 1, 4, 5. You see, this is it. This is the first row, first column. And do the same for the second one. The second one, this is going to be negative 3, 2, 7. That is the matrix transpose. 3 by 2, sorry. That is 3 by 2. 3 rows, 2 columns, and you're done. Okay, so the first, the rows becomes the column for the other one. Okay, that's first one. Get another one. Another one is going to be, if you get a B, it's a row vector. If you get a 1, -5, and 2. As you can see, this is a 3 by, okay, this is it. This is a 3 by 1, sorry, 1 by 3. That's a 1 by 3 matrix. So B transpose is going to be 3 by 1. B transpose is going to be is a 3 by 3, 3 by 1. Okay, matrix. That's it. So just switch each column into the row. So this is it. Just switch this one into the row form. 1, -5, 2. So that would be the transpose of the matrix. Okay. So this is going to be the case. Okay, so these are going to be, you may be given a square one. So I give you now 2 more, especially that last one is going to be important one. Okay, and easy one is number 3. Okay, number 3, the matrix is a 2 by 2. That's easy. So that give you -5, 3, and this is going to be 1 and -7. Quickly, we get the transpose. It's going to be 2 by 2. So the solution is going to be C transpose. This is it. You make this one into a column. 1 -7. So that's going to be the transpose. This last one is interesting. And we are going to use this property quite a lot later. Let's see what is special about this one. It's a 4 by 4 matrix. So I have 5, -6, 2, 8. And I have a -6, 3, 1, 11. And this is a -2, 1, 0, 4. And I have the 8, 11, 4, and -1. We get this one. Okay. So, and that's interesting, but it's a 4 by 4. So what's going to be transpose? If you want the transpose, you change the row into the column. You see this row? Look at this column, 5, -6, -2, 8. The second row, second column are the same. So if you get the transpose would be the same as the matrix. If two matrices, if a matrix is the transpose of a matrix, and the matrix is going to be the same, this matrix is called symmetric. And these are the type that we use in science quite a lot, especially in physics, in mechanics, okay, in future. That's quantum mechanics, okay. This would change into the kind of a special operator we call it symmetric. And you will see later on that when the matrix is symmetric, it's quite useful. So we refer to it as this type of matrix in future. But It's just a kind of introduction. We have one section on this one later on. Okay, so if you get the transpose, it's the same thing. The transpose, that's it. This is the first row. So change it to the first column. So that give you 5, -6, 2, and 8. This is the second row. It's just change it to the column. And the third one, change it to the column, -2, 1, 0, 4. And the last one, this is 8, 11, 4, -1. It's exactly the same. Okay, so we note that D transpose and the D are the same. If this is going to be the case, then we say that, and so if you like, for future observation, D is symmetric, is a symmetric. Okay, symmetric, a symmetric matrix. So if you like, you see each portion, Dij, if you like, the entry of Dij is the same as the Dgi. That's going to be the one. You see, this is going to be 1, 2. This is going to be 1, 2. This is going to be 2, 1. Okay, 2, 1, for example. This one is what? This one is going to be a 3, 3, 4. 3, 4 and a 4, 3. 4, 3 are the same thing. So that would be quite something for future application that we're going to have. Okay, so this is going to be the notion of the transpose. Taking the transpose of a function is an operator, is a function. Okay, all these operations are a special function. You give a matrix to the system, to your function, to your machine. Your function produces something for you. What is the production? It's a transpose. So this operation is function, but this function or this operation would have some very interesting properties. So we are going to give you these properties as a theorem, and you can use it anytime you like. Okay, so what is properties of the, okay, just put it over here, properties. We may ask you to confirm it by some example, not proof. The proof are easy, but we are not going to do it. What is the properties of the transpose operation? Of the transpose operation. You have to know these operations, okay? In future, we're going to do quite a lot when we get towards the end of the, end of the course. This function would have the following properties. Okay, suppose these A and B are maybe just a matrix. You see, the first one is if you find the transpose of a matrix, so means you switch the row and the column. If you do it twice, you get back to the original one. So double transpose, take you back to the original one. A transpose, switch the row and the column twice. Okay, so it's going to be one. The other one is this operation, we say it's a linear. Linear means if you have A plus B or minus B, the sum of two matrices, if you find the transpose, it's going to be transpose of the first one plus or minus the transpose of the second one. Operation that take the addition to addition and subtraction to subtraction, we call it additive. Additive operation. Okay, additive operation means you have the addition here and you have the addition outside. Okay, so that's additive property. The next one is a scalar multiplication. If you have a CA, if you multiply a matrix by 2 by 3. So what you're doing is like the derivative, if you like. If you like the limit You see, it's operation. You can keep that constant. So it's going to be C times A transpose. Okay, transpose of twice of a matrix is 2 times the transpose of a matrix. Okay, scalar multiplications. Quite interesting property again. We say this transpose is homogeneous. That's the expression that we use. Okay, so the scalar multiplication to the scalar multiplication, and this last one is quite interesting again. What would happen if you take it to the product? Remember, the product is like the composition of two functions. You see, if you want to find the transpose of two matrices, you have to switch. It's going to be B transpose times the A transpose. And the reason is the size. Remember, when you multiply, you have to have the same size to be able to do it. So when you switch the transpose here, you know that you switch the, okay, you switch the row and the columns. So that's why transpose of the A times B is B transpose times A transpose. Okay, quite interesting property and very easy to prove. We're not going to do it, just have a look at you find out that's going to be all true. But we may give you some examples to verify. Remember, you cannot simplify, you cannot prove anything in mathematics by just examples. But sometimes we may ask you to verify it for us, okay? So be ready for it. But in your book, quite a lot, that assignment that I told you. They give you various format and they want you to evaluate it. So we get quite a lot of examples. So I just give you a couple of them. Then you'll be able to go through it. But you can use these properties anytime you like. And you are going to use it quite a lot. When we get to the end of the problem, end of the course, it's going to be such an important one, okay? So transpose is clear. If you switch the row and the column twice, you get back to the original one. Addition, it's the same thing. What are you going to do when you add? You just add you're not going to change the row. This is only the tricky one is this one to prove. Otherwise, the rest are easy, okay? So that's it. Now, you have some problems to do, okay? Just show you how we're going to do it, and we are going to give one question. We put a couple of these operations. Be patient, otherwise nothing special about it. You have in that practice quiz, some of them. So we give you one question, just finding this transpose. Okay, so it is like this one. So you may be given the examples that you have. The matrix A is equal to the negative 2, 1, 3. Okay, and that's going to be 4, 0, negative 1. It's a 2 by 3. Okay, then you have a matrix B. Matrix B is 4, 1, and negative 2. Okay, and you have the 5, negative 1, 3. So this is going to be your second matrix. And they give you another one, a C, and the C, this is matrix C. Matrix C is a 2, negative 1, 2, negative 1, 0, 6. Okay, 0, 6, and this is going to be negative 3 and 2. So these would be given, and then they ask for the sum operations. Then you have to do it one by one, give us those numbers, okay? So I do a couple of them, then I continue next time because I don't have enough time. Okay, but I come back to it. So we want to compute the following. This is the type of examples that you have, and you'll be given. So compute the given expressions. Okay, that's the first part is, these are the one. They ask for the A transpose times A. The second part, they ask for the B times C then transpose. And the third part, they ask for the C transpose minus 2A. So patiently just find those numbers to put them together. Okay, so the solution, for example, if you want to find the first one, you have to find A transpose first. That's A. Switch the row and the column to get the A transpose. Okay, so the first part, A transpose, is going to be, this is 2 by 3, it's going to be 3 by 2. So this would be the first column, negative 2, 1, 3. And this would be the second column, 4, 0, negative 1. Okay, that's A transpose. Okay, you want to find the A transpose A. You have to check the size condition first. Size of A transpose is 3 by 2. Size of A is 2 by 3. So it's possible. Domain and the range are the same. So it's possible. So you check the possibility first. It may not be possible to do it. Okay, you may not be able to do it, but this is possible, so we are going to do it. Okay, so A transpose A, just the product that we talk about it, is the negative 2, 1, 3, and the 4, 0, negative 1. Then you want to multiply by A, and the A is negative 2, okay, 1, 3, and that's a 4, 0, negative 1. Okay, you multiply, go forward quickly, and this is going to be the result. Okay, you know that we get the row and you just multiply by the columns and you go on. You see, you multiply by this one, that give you 4, and 16, that give you 20. Okay, you multiply by the second one, that give you negative 2, and the 0. You multiply by this one, negative 2 times 3 would be negative 6, and negative 4 would be negative 10. Okay, and you come back and go with the second one, 1, 0, 1 times negative 2. Okay, that's going to be the 1. And over here you get the 1, and the last one we get 3. Okay, and then this one, 3 times negative 2 would be negative 6, and 4, negative 10. Again, you go the second one, 3 times 1 would be 3, they are going to be 0. And over here, 3 times 3 would be 9, 9 and 1 would be 10. So this would be A transpose A, and you're done. Okay, so it's going to be easy operation. That was the first one. The part 2. Part 2, you want to find the BC transpose. So you have to find the BC first. Okay, so you have to check the BC first. Check the size operations. This is, okay, the first one is 2 times 2 by 3. And the C is, okay, C, this is C. It's a 3 by 2. So it's possible. So you have to have a 2 by 2. It's very easy to find it. Okay, just quickly give you the solution. It's going to be 4, 1, negative 2, and the 5, negative 1, 3. You multiply by the C, which is a 2, negative 1, 0, 6, and the negative 3 and 2. And if you multiply it quickly, that give a nice 2 by 2 1. And that's what it is. It's going to be 14, 6. We can check the solution. There's a negative 2 and the negative 5. And for the transpose, you just change the row and the column to get the transpose. and be 14, 6, and then negative 2, and negative 5. So that give you know. So this is the way you have to do it when we get a problem in your book. Okay, I don't have time. I have to have another class I have to go. So I do the number part 3 later, but you can do it yourself. So that's a solution to the 3. Check C transpose minus 2A. You must arrive at this one. It's going to be negative 2, and the negative 9. And then you have a negative 9, 6, and 4. So that must be the result for the part 3. We are almost done with this section. There is only one idea that we can change. We did it already. So with this new notation, if you want to solve a system of the equation, we can summarize it and write it down as so-called a matrix equation. Okay, we call it the matrix form. So I talk about that one, okay, later on for you, and we put this operation together. That puts this section 1.4. So you must be almost to do all the problems except a couple of them from section 1.3. So quickly get them. Okay, just get the feeling of this type of operation. They're not difficult, but double check your operation. Sometimes it's messy to get these numbers. Okay, so this is the first part that we're dealing with the operation of of matrices. We're going to do quite a lot, but so far the notion of the transpose, adding, subtracting, especially multiplications. Okay, get this done. You have a couple of problems in that practice quiz that I posted for you. And of course, we give you one question dealing with this type of operations. Okay, any question, let me know. You can email me if you want to come to my office over, send me an email first, and then you're welcome to come, we can discuss the problems that you have. So have a good one and take care. I will try to give you another one for the 1.4, and I may post the solution to the practice quiz. Okay, and if I get time, I go over it together, but we do it. We have more time. Okay, have a good one. Take care. I post this one as soon as it's prepared for by the Zoom. It's going to be today. Bye bye.